Hello, this is the luckiest maths teacher in the world, and today we're looking at tree diagrams. Now, tree diagrams are diagrams useful in probability because they help you list outcomes of multi-stage events, and that's what we're interested in today. So instead of being interested in, say, rolling one dice and finding the probability of a 3 occurring, now we're interested in, say, rolling many die. We might roll 3 of them, and each roll of a dice is a different stage of the event. We might be interested in, say, tossing 5 coins. Each toss of a coin is a different stage. We might be interested in, say, drawing a card from a deck and rolling a die. So drawing a card would be one stage and rolling a die would be a different stage. So these are events that occur in different stages. So I'm going to show you how to draw one, and we're going to use the event that I toss a coin 3 times. And then what we're going to do is we're going to use this to find the probability that I get 2 heads and 1 tail. Okay, so let's go ahead and do it. So, if I'm tossing a coin 3 times, that means the event is occurring in 3 stages. So I need to leave space. I go across with each stage. So, each toss of the coin a different stage. So, let's start over here at 1. First toss of the coin. I list the possible outcomes. So I could get a head or a tail. I list them going down. Now, if I get a head on the first go, on the second go, I can still get a head or a tail. Similarly, if I roll a tail first up, I can still get heads or tails on the next go. And for the third toss of the coin, it's the same thing. Doesn't matter what I got in the previous 2, I can get heads or tails on the last one. Okay? Now what you notice here is that each time I toss the coin, the total number of outcomes doubles. So there were 2 possible outcomes after 1 toss of the coin. If I toss the coin twice, there are 4 possible outcomes. If I toss it 3 times, there are 8 possible outcomes. So what you do at the end of your tree diagram is list the outcome by following the branches, hence the name tree. So I've got here head, head, heads. So that's my first outcome. Okay, I can also go head, head, and then tails. So that outcome, I write here, head, head, tails, and I keep doing this for all of the outcomes. So this is a convenient way to make sure I've listed all the outcomes. Okay, and there are just a couple more tail, tail, head, and tail, tail, tail. Now, in this one, you can see there are 8 outcomes, and each of them is equally likely because each time I toss the coin, heads and tails are equally likely. So each of these 8 outcomes has a probability 1/8 of occurring. So the probability of getting head, head, heads is 1/8. Now, to answer the question, what's the probability I get 2 heads and 1 tail? Well, I've just got to look through my list of outcomes and find which ones have 2 heads and 1 tail. So this one certainly does, but so does this one. 2 heads and 1 tail. This one has 2 heads and 1 tail as well, and you can see that they're the only ones. All the other ones either have 3 heads, 1 head, or no heads. So the probability of getting 2 heads and 1 tail is very simply 3, because there are 3 ways it can occur, over 8, because there were 8 outcomes in total. Now I just want to do one more tree diagram to show you what we do when events at each stage are not equally likely. Okay, so I'm going to use a tree diagram to solve this problem here. So I randomly pick 2 cards from a deck. I do it one after the other without replacement. And what's the probability I get 1 and only 1 picture card? Now this is a multi-stage event because I'm picking 2 cards. I pick one, don't replace it, then pick another. So that's why a tree diagram is appropriate here. Now, one thing I haven't mentioned is that each stage must be independent of the last. I know it's a hard thing to get your head around, but if I say pick a picture card the first time, though the probability of getting a picture card the next time changes, that second pick is independent of the first pick. Picking the picture card out of the first one doesn't influence me picking a picture card in the second go. Okay, so hopefully that'll become clearer as the example goes on. To start with though, we need to know what a picture card is. Well, that just means a queen, king, or jack. Okay, so we'll set up our tree diagram just like we did in the previous example. So 2 stages. Each stage is this time a pick of a card. So there really isn't any point me listing all of the outcomes, like ace, 2, 3, 4, 5, blah, blah, blah. There's too many of them. All I'm interested in this question is whether the card is a picture card or not a picture card. So I'm just going to put P for picture card and P complement, which means not P for not a picture card. And of course, if I get a picture card first time, I could get another picture card or not. And similarly for not P. Okay, now, just like I did in the previous example, I'm going to list the outcomes. So there are sort of 4 possible outcomes here, right? So it looks pretty straightforward. Now, it might be tempting for you to then say, oh, okay, cool. So the probability that I get one and only one picture card is this one, a quarter plus a quarter, which is a half. The problem here is, though, that each of these is not equally likely. P and not P are not equally likely. So what I do in these cases is I need to write on the branches the probability of each occurring. So I draw an extra branch for the first go because I need to write the probabilities. Now, in a deck of 52 cards, there are 4 queens, 4 kings, and 4 jacks. So there are 12 picture cards all up. So, if I pick a card from a random deck, the probability it's a picture card is 12 over 52, and that simplifies to 3 over 13. So the probability that I do not get a picture card would be 1 minus 3 over 13, or 10 over 13. Okay? Now, the probabilities change in the second go because I didn't replace them. So, if I have got a picture card, so there were 12 out of the 52. Now I've taken one away. So there are 51 cards left, but because I've already taken a picture card, there are only 11 picture cards in the deck. So 11 are picture cards and 40 are not picture cards. So for the next one, if I didn't get a picture card first up, there are still 12 picture cards, but there are 51 cards in the deck because one of them has already been taken. Now, if I started with 12 picture cards, there were 40 that were not picture cards. If I take one of those, there are 39 left out of the 51. Okay? So, all of these 4 outcomes here will not be equally likely. They have different probabilities. Now, I said that each stage, the events have to be independent. So this event here is independent of this because we've already accounted for the fact that there are fewer picture cards. So to find this outcome PP, I just need to multiply, because they're independent, and we went through this last time, I just need to multiply the 2 probabilities together. So the probability of getting 2 picture cards in a row is 3 over 13 times 11 over 51. Okay? So, this outcome here, to get a picture card and then not a picture card, again, I just times first probability by the second probability. So this would be 3 over 13 times 40 over 51. Okay, and then to find this outcome here, again, I just follow the branches and multiply the probabilities. 10 over 13 times 12 over 51, and same for the last one. 10 over 13 times 39 over 51. Okay? So I just figure out what each of these equal now. So I'm just going to use decimals now. I'm rounding, it's close enough, and I'm just going to write these in. They just come from your calculator. So the probability of getting 2 picture cards in a row, if I multiply them together, it's about 0.05 to 2 decimal places. And the next one, if I do that, I get approximately 0.18 again to 2 decimal places. And the last two, so that's 0.18 as well, and this one is 0.59. Now notice that all of these should add to 1, because the probability that one of them happens is 1. It's certain that one of those outcomes will occur. So they do in this case. 0.05 plus 0.18 plus 0.18 plus 0.59 does equal 1. So I know I'm doing something right. So then what's the probability that I get one and only one picture card? Well, they are these events here. One picture card only, one picture card only. This one has 2 picture cards, this one has none. So using what we learned last time about the OR rule, the probability that I get one and only one picture card is the probability that this happens, or the probability that this happens. So the answer to the question is going to be 0.18 plus 0.18. Now, notice that in any tree diagram, all of these outcomes will be mutually exclusive. You can't have more than one of them. I can't get a picture card, then a non-picture card, and at the same time get a non-picture card, then a picture card. So all of these outcomes here are mutually exclusive. So the probability that I get one and only one picture card, I can just add the 2 probabilities together. I don't need to worry about the probability they both occur. And so the answer I get is about 0.36. Hope you've enjoyed the video. This has been the luckiest maths teacher in the world. Have a great day.